function of a neutral in a three-wire system. This exercise will demonstrate how opening a neutral impacts current flow and voltage in a three-wire system or circuit. Take note of the three ammeters. They are wired in series with A phase on the left, black, B phase on the right, red, and a neutral in the middle, white. At present, no load is turned on and the neutral toggle is closed. When the A phase is energized with a load, a slight deflection of the analog needles is seen on both the A phase ammeter and the neutral ammeter. Since no load is energized on B phase, no current reading is seen on the B phase ammeter. When the B phase is also energized with an identical load, there is no significant current on the neutral ammeter, as an equal value of current is read on both the A phase ammeter and the B phase ammeter. When the loads on A phase and B phase are not equal, the neutral carries the difference, or unbalanced current between the two loads. Residential and small commercial establishments typically follow a 240, 120 volt single-phase system. The potential between the ungrounded conductors is 240 volts. The neutral is center tapped between them to create a 120 volt potential between it and each ungrounded conductor. Loads are located to balance the current on each ungrounded conductor as equally as possible. The impact of the neutral opening will now be demonstrated on a typical residential circuit. The circuit shown is that of the first 5 circuits of a house. The breakers labeled R1 through R5 are attached to a space heater, a 100-watt light bulb, a hairdryer, a 40-watt light bulb, and an electric water heater. The fork meter will demonstrate the current and voltage on the loads of a 3-wire system and the role of the neutral. Press the Open Schematic button at any time to see a reference sheet of all the currents and voltages in the system. The schematic will be updated throughout the module as the fork meter takes readings. With one meter lead attached to the neutral terminal and one attached to the R1 terminal screw, we can see the voltage is 120 volts. This should be the same on all single-pole breakers under normal conditions. Moving the lead through the remaining single-phase breakers, we can see they are all 120 volt. Switching to amps, we can see the current on R1 is 10 amps. When the fork meter is moved to R3, the current measures 15 amps. Moving the fork meter to read the current flow through the remaining single-phase resistors, we see 0.83 amps through R2 and 0.33 amps on R4. Moving on to the last resistor, we read 16.67 amps on R5. Switching to the volt setting and placing our leads across R5, the fork meter shows it is receiving the total voltage of the sources, which is 240 volts. This is a common type of load connected from ungrounded conductor to ungrounded conductor, or phase to phase. When the fork meter is moved to measure the load on the neutral, the unbalanced current is 4.5 amps. With the neutral in place, all appliances are acting as normal. Note that only the first 5 breakers are switched to the on position, so reading from the main neutral feed allows us to see the neutral current for just the first 5 breakers. With the neutral removed, indicating an open neutral occurrence, voltage and current increase on R1 and R2. Loads that receive more voltage and draw more current than before may shine brighter, overheat, and possibly even cause a fire. Loads receiving higher values could possibly short or at least have a decreased lifespan. Loads seeing lower values will dim or just fail to work. R1, 2, 3, and 4 were designed for 120 volts. While R1 and R2 see higher voltage, R3 and R4 see lower values. The current through them is also affected. R5 was designed for 240 volts and is the only load unaffected. The previous examples demonstrated the importance of the neutral. This table shows the values before and after removing the neutral from the circuit.